OCR Chemistry A, neutralisation. We'll start with the various pH curves seen in titration, move through equivalence point theory, indicator theory, and the use of a pH meter. There are 4 possible combinations of weak and strong acids and bases. We can have a strong acid and strong base, a strong acid and weak base, strong base and weak acid, and of course a weak acid and a weak base. Now, each of these titrations produces its own typical pH curve, which as an A-level chemistry student, you'll be expected to be able to recall, sketch, or interpret. Now, as a starting point, we're going to start with the strong acid and strong base titration. And I'm going to ask you to calculate the pH changes during that titration process. So we're imagining that 25 centimeters cubed of 0.2 mole per decimeter cubed hydrochloric acid is titrated with sodium hydroxide solution at the same concentration. Now, here's the initial volume of hydrochloric acid, 25 in each case, and in a titration from the burette, you add various volumes of sodium hydroxide. So 0 centimeters cubed, 5, 10, 20, 24, 25, 26, 30, 35, and 40. I'd like you to, after I have modeled a couple, I'd like you to calculate the pH that would result from each of those additions of volumes of sodium hydroxide. But to start with, we'll say, or we'll model the calculation of the first two. So as hydrochloric acid is a strong acid, the concentration of hydrogen ions will equal the concentration of the acid. So the concentration of hydrogen ions is also 0.2, as that is the concentration of the acid. We put that into the pH definition, and that comes out as 0.7. Now for the second pH, we need to calculate the excess moles of hydrogen ions. Now, the easiest way to do that is to realize that 5 centimeters cubed of sodium hydroxide at 0.2 will neutralize 5 centimeters cubed of hydrochloric acid at 0.2. So the simplest way of carrying out this calculation is to say we have an excess of 20 centimeters cubed of hydrochloric acid at 0.2 moles per decimeter cubed, which tells us the excess moles is 0.004. So I have said in my method that the addition of 5 centimeters cubed of sodium hydroxide neutralizes 5 centimeters cubed of hydrochloric acid as they're at the same concentration. So I'm left with 20 centimeters cubed at 0.2, which gives us that numbers of moles. Now, the concentration of hydrochloric acid depends on the numbers of moles and the new volume. So the new volume is 30 centimeters cubed. 25 and 5 makes 30. So my concentration of H+ ions is 0.133, and therefore the pH is 0.87. Carry out the calculations in the same way for 3, 4, and 5. Pause, complete the calculation of pH, come back to check your answers when you are ready. So here are the calculated pHs. As we said, 0.7 for initially, 0.87, 1.06, 1.65, 2.39. If you did not achieve those pH figures, please go back and carry out the calculation again. The model is printed below. Now, when we've got complete neutralization, the concentration of H+ ions is due entirely to the dissociation of water. So we're assuming, although I haven't stated it, that we are at 25 Celsius. So the pH at complete neutralization would be 7. So I'm going to model the calculation of pH when we have an excess of sodium hydroxide. So we need to work out the excess hydroxide ions. So we're going to use the same method, that is, we have 25 of acid and 26 of sodium hydroxide at the same concentration. So we have an excess of 1 centimeter cubed of sodium hydroxide at concentration 0.2, which gives us 2 times 10 to the minus 4 moles excess hydroxide ions. From that, we need to move to a concentration. So we're dividing the numbers of moles by the volume. The volume is 25 plus 26, which gives us 3.92 times 10 to the minus 3 moles per decimeter cubed. That's the concentration of hydroxide ions, from which, using Kw at 1 times 10 to the minus 14, dividing by the concentration of hydroxide ions, we achieve the concentration of hydrogen ions at 2.55 times 10 to the minus 12. Plug that into the pH definition, gives us a pH of 11.59. So there is the model calculation for titration 7. Could you calculate the pH for 8, 9 and 10? Come back to check your pH answers against mine when you are ready. So here are the pH numbers for the excess sodium hydroxide. I've rounded 11.59 to 11.6, 12.3, 12.5 and 12.7. If you achieve those pH figures, well done. If not, go back through your working until you achieve those correct answers. Ideally, you have a piece of graph paper to hand or an online graph paper, and you are able to plot the pH on the y-axis against the volume of sodium hydroxide added. So the volume of sodium hydroxide will run from 0 to 40, and the pH will run from 0 through to, shall we say, 13 or 14. I'd like to see a plot. I'd like you to plot that pH against the volume of sodium hydroxide. Take your time, pause the lesson, obviously, come back to check against my plot when you are ready. So if we plot the points that we calculated on the previous slide and apply a best fit line, we see the typical curve for a strong acid, strong base titration. So here we're adding a strong base into a strong acid or against a strong acid. Now, how would we recognize this? Well, we can see here that we're starting at a low pH. So that certainly implies that we're starting with a strong acid. We get a vertical part of the curve. We get a vertical change in pH. And then we reach a high pH here. So that would tell us that we have an excess of strong base. So what's typical about this titration curve is the low pH starting point, which tells us we start with a strong acid. Then we have a vertical change. And then we have a finish with a high pH, which tells us that we have a strong base. So that curve is typical for any strong base against a strong acid. So if we now move on to a strong base against a weak acid, we can see the characteristic curve set out on the screen. We have a vertical section of pH change. We have a high pH when we have an excess of strong base. So we've got a pH value of around about 13, something like that, towards 13. But we know that we've got a weak acid initially because look at the starting pH. We've got a pH of about 3 for the original acid solution. So that would imply that we have a weak acid. So typical features for a strong base into a weak acid, starting at around about pH 3 to 4, somewhere rather than 1 or 2 for a strong acid. So this is a weak acid as indicated by the initial pH. We have a vertical section of the pH change curve around, in this case, around 25, because we're starting with 25 of ethanoic acid and we're adding sodium hydroxide of the same concentration. But we know we've got a strong base because we're ending with a high pH. So this is typical of a strong base against a weak acid. So moving on to a weak base against a strong acid. Again, we're starting with a strong acid, so we start with a pH 1 or below. So we know we're starting with a strong acid. There's very little change or relatively little change in pH. Then there's a vertical section. Then there's a gradual change to a pH value of around about, in this case, around about 10, which tells us that we've got an excess of weak base. So we saw with the strong base that the pH was more up around 13, somewhere it would be up here. But with an excess of weak base, we have a pH of around about 9, 10, somewhere like that. So this is typical of a pH curve for a weak base into a strong acid. So in this case, ammonia titrated into 25 centimeters cubed of hydrochloric acid. So again, they're at the same concentration or equal concentration. So we would expect to see the vertical part of the curve, the pH change curve, at around 25 centimeters cubed. And finally, we'll move on to a weak base into a weak acid. Now, what's distinctive of this is that you will immediately notice there is no vertical section to the pH change curve. However, we know it's a weak acid initially because the pH is initially around about 3, and we know it's a weak base because once we have excess base at the end of the titration process, we've got a pH of around about 9 or 10. But what is particularly distinctive of weak base and weak acid titrations are that there is no vertical section of the curve. The meaning and determination of equivalence point. So the equivalence point is the point in an acid-base titration at which exactly the correct amount of base or acid has been added for complete neutralization according to the chemical equation. So sodium hydroxide and hydrochloric acid gives us sodium chloride and water. So the same numbers of moles of sodium hydroxide as hydrochloric acid have been mixed together. So we have complete neutralization. Therefore, at the equivalence point, the only two things present in the conical flask in which you are titrating acid and base is the salt and water. So at the equivalence, there is no excess sodium hydroxide, there is no excess hydrochloric acid. You've got exactly reacting amounts, exactly reacting moles of acid and alkali or base. Therefore, the only thing present is the salt and water. Now, assuming, and this is the case for OCR Chemistry A, assuming monobasicity of acid and base, at the equivalence point it is true to say that the moles of acid equal the moles of base. So if we can continue to consider sodium hydroxide and hydrochloric acid at the same concentration, and as per our earlier calculation, we've got 25 centimeters cubed of hydrochloric acid. It's a 1-to-1 reacting ratio in the balanced equation. So the equivalence point, that is when you've got exactly reacting moles of sodium hydroxide and hydrochloric acid, will be when 25 centimeters cubed of sodium hydroxide is added. We've got 25 of hydrochloric acid. The sodium hydroxide is at the same concentration, therefore we will have the same number of moles, exactly reacting moles, when 25 centimeters cubed of sodium hydroxide is added. And we will notice that that corresponds to the vertical section of the pH change curve. So we can determine the volume at which equivalence is achieved by locating the vertical section of the pH change curve and reading off the volume of sodium hydroxide added in this case. Now the pH at equivalence would be expected to be pH 7. Now you may or may not realize that that is not necessarily the case. The key point is that sodium chloride is a neutral salt. So there's no sodium hydroxide at equivalence, it's all been reacted. There's no hydrochloric acid, it's all been reacted. The only thing present in solution is sodium chloride. Sodium chloride is a neutral salt, it has no acid-base properties. Therefore the pH at equivalence is 7. And you'll find that that is positioned halfway or in the midpoint of the vertical section of the pH change curve. So the pH at equivalence can be found midway in the vertical section of the pH change curve. So let's consider a weak acid having a strong base added to it. So sodium hydroxide and 25 centimeters cubed of ethanoic acid at the same concentration. Now we would predict or expect that the equivalence point would be when 25 centimeters cubed of sodium hydroxide is added. That is when we will have exactly reacting moles of sodium hydroxide and ethanoic acid. And that again corresponds to the vertical section of the pH curve. So from the pH curve, we can read off the equivalence point volume. But what about the pH at equivalence? Well, that's the midpoint of the vertical section of the pH curve, and you'll notice that does not correspond to pH of 7, but is weakly alkaline, a pH of 8 and a little bit, 8 point something. Now, why is that? Well, we have to consider the acid-base properties of the salt that is formed. Sodium ethanoate is a basic salt. The ethanoate ions released by the dissociation of sodium ethanoate is a proton acceptor. So the concentration of hydrogen ions is decreased by the presence or combination with the ethanoate ion, and therefore an alkaline pH is found at equivalence. So on determining the pH at equivalence, you need to consider the acid-base properties of the salt that is formed. Now, one little additional point is that this section of the pH curve is often referred to as the buffer region. You'll see that there's an initial increase in pH, but then that increase is minimized. That's because in this section, the buffer region, we have both an excess of ethanoic acid, but also the presence of the salt. So in this region of the titration here, we have both some ethanoic acid remaining unreacted and the salt that is formed. So we have weak acid and the salt of the weak acid. So that's our recipe for a buffer. So the pH does not change greatly here because of the buffering effect of the solution being formed. So working our way through, let's consider adding ammonia, a weak base, to 25 centimeters cubed of a strong acid, hydrochloric acid, both at the same concentration. You'll see that we would predict the equivalence point to be when 25 centimeters cubed of ammonia is added. It's a 1-to-1 reacting ratio. So the numbers of moles of ammonia and the numbers of moles of hydrochloric acid be the same at equivalence. And that again corresponds, that volume again corresponds to the vertical section of the pH change curve. Now, what about the pH at equivalence? Well, the midpoint of the vertical section of the curve gives us a pH of a little below 6, so it's weakly acidic. That's because ammonium chloride is an acidic salt, so we need to consider the acid-base properties of the salt formed. The ammonium ion is a proton donor, so a solution of ammonium ions is weakly acidic. Indicator theory. So moving on to indicator theory, we're going to regard indicators as weak acids that have two differently colored species in their dissociation equilibrium. So if we think of our weak acids as HA, H plus and A minus are formed by the dissociation, but HA might be red and the conjugate base A minus might be blue. If we have this situation, then this acid has the potential to be a useful indicator. Now, this equilibrium is of course subject to Le Chatelier's principle. That is, changes in the concentration of hydrogen ions will shift the equilibrium to the left or to the right. In other words, towards the red or towards the blue. So, predict and explain, using Le Chatelier's principle, what will happen if acid H plus ions are added to a solution containing the indicator in above. Pause, write out your explanation in bullet points, come back to look at mine. Okay, so my argument runs like this. If you add acid, you're increasing the concentration of hydrogen ions. Therefore, the equilibrium will move to the left to counter that increase. That's using Le Chatelier's principle. That means the concentration of HA is increased and the concentration of A minus is decreased, and therefore red would be the dominant color. Okay, so again, using Le Chatelier's principle, predict and explain what would happen on adding alkali hydroxide ions. Write out your answer, bullet points or numbered points, and then come back to check against mine. Okay, so here's my argument. The added hydroxide ions react with hydrogen ions. Please note, we need to affect the concentration of hydrogen ions. Hydroxide ions do not appear in this equilibrium equation, only hydrogen ions. So hydroxide ions react with hydrogen ions, reducing the concentration of hydrogen ions. Therefore, the position of equilibrium via Le Chatelier will move to the right to counter that decrease. So, the concentration of acid HA will decrease and the concentration of A- will increase. Therefore, blue will be the dominant color when alkali is added. Indicators change color at a particular pH, and the pH around which indicators do change color is referred to as the indicator endpoint. And we can calculate that from Ka values. So indicators are weak acids, they will have a Ka value. If we look at the Ka expression for a generalized weak acid HA, the color change point will be when the two colored species have the same concentration. So the concentration of HA and the concentration of A- will be the same. That is only true at the indicator endpoint, which is when the color changes. So to transition from one color to the next, we must go through a point at which the two colored species are there at the same concentration, and we call that the end point. Therefore, those two concentrations will cancel out, leaving us with Ka equaling the concentration of H+ ions. In other words, pKa minus log to the base 10 Ka will equal minus log to the base 10 the concentration of H+. So pKa equals pH at the indicator endpoint. So the pKa value for an indicator tells you the pH at which the color change occurs. Now, the eye, the human eye, cannot detect the indicator endpoint. Generally, a 100-fold change in ion concentration is needed for the human eye to detect a color change. That corresponds to about a 2-unit change in pH. If you remember, pH is a logarithmic scale. So pH unit 1 either side of the endpoint pH. So the indicator range, if we look at some examples for, say, for methyl orange, which has a pKa of 3.7, in other words, the pH of the endpoint is 3.7, so the pH range is found to be 3.2 to 4.4. Approximately, at A level we will say approximately 1 pH unit either side of the pKa or pH at endpoint value. Bromo-cresol green, pKa value 4.7, so the indicator endpoint at pH 4.7, the range 3.8 to 5.4. These are from a data book, but they follow the trend of being one above and one below the indicator endpoint pH. So phenolphthalein, pKa 9.3, so endpoint pH 9.3, pH range 8.2 to 10, and then alizar in yellow, pKa 12.5, pH at endpoint 12.5, range 10.1 to 13.0. So indicator range is one above and one below the indicator endpoint pH, which corresponds to pKa. pKa and pH have the same value at the indicator endpoint. Indicator choice for particular types of titration. So indicator choice depends on making sure that the indicator is useful in a particular titration. And to be useful, an indicator needs to change color on the addition of a drop or one or two drops of titrant. And the color change volume, the volume at which the indicator changes color, should correspond to equivalence. For these two requirements of usefulness to be met, the vertical section of the titration pH curve should pass through the indicator range. So let's look at the choice for a strong acid being added to a strong alkali. So we're starting with a high pH initially, so we've got a strong alkali, and then we're ending with a pH of about 1, so in excess acid we have a strong acid. Obviously we have a vertical section of the curve. If we mark in the vertical section of the curve, we need that to pass through an indicator range if that indicator is to be useful. So if we look at phenolphthalein, the range is 8.2 to 10, and indeed the vertical section of the pH curve does pass through the indicator range. So as we add hydrochloric acid here, drop by drop, we will get a rapid pH change at equivalence, which corresponds to the vertical section, and the indicator will change color because the pH has moved from around about, according to my graph here, around about 11 through to around about 2.5 or something like that. So phenolphthalein will change color because the pH has passed through its range. Now what about methyl orange? Well, methyl orange has a range 3.2 to 4.4. Again, the vertical section for a strong acid, strong alkali will pass through the range of methyl orange. So the addition of 1 or 2 drops of acid will cause a large pH change, and that pH change will pass through the methyl orange range, and therefore methyl orange will change color when 1 or 2 drops of hydrochloric acid are added. So both phenolphthalein and methyl orange meet the requirements to be a useful indicator for a strong acid and strong base titration. But what about a strong base being added to a weak acid? Well, if I mark in the vertical section, I need an indicator whose range corresponds to that vertical section. So let's look at phenolphthalein, 8.2 to 10. Yes, the vertical section of the pH curve does pass through the phenolphthalein indicator range, and therefore as drops of sodium hydroxide are added around the equivalence point, a rapid pH change will occur which will change the color of phenolphthalein. So phenolphthalein is a suitable indicator. If we contrast that with methyl orange, 3.2 to 4.4, we'll see that to affect the change of color of methyl orange, we need to go from 3.2 to 4.4. Well, we're going to have to add around about 20 centimeters cubed of sodium hydroxide. So that does not change, methyl orange will not change color on the addition of 1 or 2 drops, nor will its colour change indicate the position or the equivalence volume. So only phenolphthalein is suitable as its indicator range matches the vertical section of the pH change curve. Moving on to a weak base being added to a strong acid and marking the vertical section. Phenolphthalein, methyl orange. Pause and decide which of those 2 indicators is suitable for this titration. Okay, so I'm hoping you will see that methyl orange, the vertical section of the pH change curve, passes through the range for methyl orange. So that is a suitable indicator. The range for phenolphthalein is at a higher pH than the vertical section of the pH change curve. So phenolphthalein is not suitable. Methyl orange is suitable for a weak base into a strong acid. If we now look at a weak base into a weak acid, the absence of a vertical section to the pH curve means that regardless of the indicator range, indicators will not be useful in finding the equivalence point for acid-base titration if they're both weak acids and weak bases. Other methods have to be used which are not on the OCR Chemistry A specification. Unusually, for the OCR Chemistry A specification, the instrument, a pH meter, is specified, the techniques and procedures for its use. So I've covered it on the next 2 slides. So you will probably have used a pH meter in PAG 11.2 and PAG 11.3, that is producing pH change curves in titrations or forming buffers. You have essentially a probe and a meter, probably with a digital readout. But before its use, and I think this is what must be meant by in the specification, the pH meter must be calibrated. So calibration of pH meters in schools is generally what's called a 2-point calibration. So you start with the process of cleaning the electrodes, which is essentially with distilled water and lint-free tissue. Then you calibrate with a pH at a buffer at pH 4. Then you calibrate your meter with a buffer at pH 10. Now the pH meter is ready to use to measure the pH of other substances. In between the pH measurement for different substances, you should rinse with distilled water. I think that will just about cover all possible marking points.